Welcome, everyone. Thank you for coming. I'm going to have two talks today. They are going to be back-to-back, so there's going to be a break, but they're not going to be in the same room. So right after this talk, I will go up to room number 4 to set up. So there will probably be no questions. If you want to ask questions, just follow me up to room 4, and then I can talk while I set up. Okay, so the first talk is isolating GPU access in its own process. And my name is Patricia Aas. I'm now a consultant, now for like 3 weeks. I'm a C++ programmer. I'm hoping to make something in between C++ and application security. I just recently left Vivaldi, where I worked on the Vivaldi browser. Before that, I worked at Cisco doing telepresence systems. Before that, I was a Java consultant for a couple of years at Knowit, and before that, I worked on the Opera browser. I have a master's in computer science, and while I was studying, I basically programmed in Java mostly and different other types of languages. So my first C++ experience was starting at Opera, which is now 13 years ago. So there will be a little bit of an introduction to the area, and I've spread it over these two talks, introducing the concepts that I think are important for the talk. So they kind of follow each other because they're both about Chromium. So to give an idea of what Chromium is, so I will give you a little bit of browser history. So the major browsers today all have a long lineage that goes back to the 90s in general. And all of these browsers that you probably know all originate with the KHTML engine, which was used in Conqueror and made by the KDE project. And so in the early 2000s, Apple forked it and called it WebKit and used it to make Safari. A little bit later, Google chose to use it to make their Chrome browser. It was in 2008. And they cooperated on the WebKit project for quite a few years. But after a while, Google found out or decided that maintaining the compatibility was a lot of work, and they were basically doing most of the work on WebKit, and decided that it would be easier for them to do a fork. And so they did a fork of WebKit, and that is what is called Chromium Blink. Now, the Chromium part is actually around WebKit. So WebKit is a web view kind of thing, and Chromium is the framework around. So I can go back. So I will look a little bit about how that works, because it impacts how composition works. And I will talk about it even more in the next talk when I talk about sandboxing. So composition. A lot of people who haven't worked on low-level UI are not familiar with composition. But basically, in a Chromium-based browser, you have massive composition because you have many processes. And you've probably seen this doing PS or something on your machine, and your browser has started maybe dozens or hundreds of processes. And all of these processes, or most of them, are producing some fragments that are used to compose the browser window. And so composition is trying to stitch all of this together to one view, one browser window with tabs and things, right? So I just quit a browser company, and I just might have made a small browser. But it was basically a little bit for beginning for a project that I'm planning on doing, which has to do with security, but it was also a little bit about this talk. And I might have decided to do a demo last night, maybe at 1 o'clock in the morning. So let's see how this works out. Okay, so, well, we'll wait for that one. Okay, so we'll start with this one. And one of the things that I think is really, this is, let's see here. Okay, no. There we go. So this is my browser in high resolution. This is a CSS demo. which I find is very cool. It has animations, it does all sorts of things. And the reason why I want to show you this is because I'm going to show you how this is composed. So let's see here. So let's instead look at this in the background. So in this case, the browser that I made is Qt-based. It uses the Qt web engine, which uses Chromium Blink. But Qt has this feature where you can show the composition layers in this overlay. So this three-dimensional box here represents the browser behind it. So if I do like this, then you can see the layers being moved around. And you can rotate the box behind, or the sphere behind, and you can see that the layers move. And the reason why I want to say this is these are the different layers that are produced by the web view. And in this case, there might be hundreds of them, right? And they have to be composed together to make just the web page. And then this also participates in the full browser. So the green stuff on top is my address bar and my tab and things. So green here is something that is opaque. Red is something that has some sort of alpha. So composition is in modern applications is very complex, much more complex than most people think. Okay, and let's see. So I'm going to have here is a video that I'm showing. There's nothing really on this page, and here you can see that the video is a floating opaque layer on top of this background, and this background is these checkered things. Now, if you want to research more into Chromium composition, you will see that this is some of the optimizations done there to give good scrolling. But let's go back to the presentation. Okay, so you have an idea on all of the layers, and they are layers upon layers, and everything has to be stitched together, and this is composition. And in the original Chromium, the architecture looked a little bit like this. So Google decided to put WebKit in its own process. And the reason for this is a little bit that they didn't have control over the stability of WebKit. WebKit could crash. And putting it in its own process meant that if it crashed, it could be restarted without bringing down the whole browser. So in general, you can think that there's one render process per tab. And each of them produces a web page, which could be very complicated and complex with many layers. But then you have many web pages. And again, that has to be composed together with the UI. And in the beginning, they did this with software composition, which was done in the browser process, which is like the original, the one that you start when you start the browser. Later, they moved over to a hardware composition architecture. And now you had to submit the layers to the hardware composition, which was placed in its own process, which is called the GPU process. Now, given that you have so many applications, you need some kind of communication, and you need a startup sequence to make all of these things. And the startup sequence I'll look at a little bit more in the next talk, but you see the process relationships a little bit like this. So you have a browser process, which is the one you start, which could be Chrome, Opera, Vivaldi, Brave, whatever. And it will make two children, what I call Zygote init, and this GPU process, and those will again make other child processes. And at the bottom there, you see the renderers, which are roughly equivalent to a tab. And those are, so the solid lines are the process kind of relationships, but the dashed line shows that there should be dashed lines everywhere, because there are massive amounts of communication that is done. But in this case, you can see that both the renderers and the browsers need to communicate to the GPU process. And to do that, they use a bunch of different facilities. Now, the whole talk is Linux-based, and I'm pretty Linux-based. So in this case, they're using shared memory. And in shared memory, they have something they called command buffers, which is basically a section of shared memory that they treat as a ring buffer. And they put serialized GPU commands. We'll get a little bit into that. And other types of memory objects can be placed also in shared memory. And then you have these IPC channels to the GPU process, which are basically pipes, right? So this is the general architecture to be able to do this. Because the thing is that the API for dealing with graphics inside of the renderer process and also in the browser process is OpenGL ES2. And this is generally the mobile kind of API for graphics. And many places you don't even have OpenGL. But this is the interface that these applications program against. And they do that by having an OpenGL ES2 interface that they program against. And they use roughly normal OpenGL ES2 commands. But this is really fake. It's a very thin layer, which goes to this encoder, which basically takes the commands, function calls, serializes it, and places them in this ring buffer, this command buffer. And that buffer, again, is read by the GPU process, which deserializes these commands, validates and does maybe transformations, and then actually executes them. Now, it could be that they are executed on something that's not even OpenGL, because these things are now decoupled. So this is the architecture, this is the idea. And what you see here is that you have many possibilities of injecting your own logic in this chain, and that is used a lot. So basically you have a client, which could be the renderer or the browser, for example, and they will do OpenGL ES2 function calls, which results in these command things that are serialized into the command buffer, and then they signal the GPU process that they put something there, and then on the GPU side, you have many of these command buffers that you're dealing with, because you have many clients, many renderers, and one browser. And so you will have to pick commands off of the queue, validate the arguments, maybe do some transformations, do things, and then make the actual underlying call. What you see clearly, if we go back, is that there is a decoupling in both time and space here. So you make a local function call, but you don't know exactly when this will finish or when it is finished executing. Now this is true for many graphics APIs, so it's not a strange concept. So the conceptual model of this, though it isn't how it's implemented, but this is the conceptual model of it. You have a client on one side, the server on the other side, and then you have things that they call like the IPC channel, then the command buffer that I talked about. Then they have something they call a command stream. And inside of a command stream, you can have several command buffers. And you can have several command streams inside of an IPC channel, and so this can get kind of complex. So when it gets complex, you need some kind of synchronization architecture. And they use something they call a sync token. Now, what you will see often in Chromium is that you have very high-level abstractions. And that is because you have a very diverse set of architectures that you're faced with. And so you have to implement many things specifically for each platform. So the idea of a sync token is that it is a synchronization fence that you put into the command stream. And then someone can wait on that fence. And I'll show you a little bit about that. So a sync token is quite a simple thing. It belongs to a command buffer, and it belongs to a command buffer namespace. It is a very simple object, really. And so here you can see a more of a complicated version where you have here the browser command stream on top. Then you have two renderers that have actually two command buffers each. And here you have the different types of synchronization primitives. So the big blue box in the middle is an ordering barrier. It's a simple one, but it basically, what you clearly see is that within a command buffer, the order of the commands are sequential. You put one in, and then you put another in, and they will be handled FIFO, right? So you will take them as they go. So they have a sequentiality. You know that when it's your turn, what was before you has already been handled. But when you have multiple command buffers or multiple streams, you don't know. So when you start having dependencies that span these streams, then you start having to introduce synchronization between them. So ordering barrier is a simple one that you can use if you are both in the same IPC channel or in the same command stream. But if you are spanning two command streams, you can use something they call an unverified sync token. And the idea here is that this wait sync token will not be processed. The wait sync token won't be processed until the sync token has been signaled. So the idea here is that you know that when the sync token has been signaled, everything before it has already been processed. So this is a way of making sure that what is after the wait sync token comes after the commands. And the same idea here with the verified sync token, which is a little bit different, needs to be signaled across and things like that. But it basically, you can promote an unverified sync token to be a verified sync token and do the same thing. And I will show you an example of when that is necessary. And that is in this example here. So here we are going to look at passing a video frame and composing that. So we're going to look at software decoding. Now, in Chromium, there are basically two ways of decoding video. You have software decoding, which was the way it was the traditional way, or the way it was done since the beginning. And then you have slowly but surely introduced some hardware decoding. Hardware decoding is done on the GPU in the GPU process. So we're not going to look at that because it doesn't really, it's not as fun. So in this case, you're doing software decoding. And software decoding in Chromium is done by FFmpeg, and it's done inside of the renderer process. So now you have a decoded frame in memory inside of the renderer process, but you need it on the GPU. And so we're going to look at how you're going to do that. Yeah. Now, the first part is fine. It's very synchronous. You decode the frame into render memory, and you're good. You know, you have it in render memory. But now you need to copy the frame to the GPU. And later on, at some point, when you have to paint the frame, you have to actually issue the draw commands to say, OK, I want to paint that texture that you got earlier. The thing is that the issuing of the draw commands will generally come from the browser process, and the copying of the frame is copying from the renderer process, and these things are desynchronized. So you have to make sure that by the time you ask it to draw this thing, that it is actually there. So in this case, you will have this sync token that you have to kind of carry around to make sure that you are waiting for that, waiting for the frame to be available on the GPU before you issue to draw it. I will show a lot of diagrams for this, and you don't really have to care unless you want to read the slides later about the details, but it's basically to show this kind of process. And even this small little line that I will show you on tracking this video frame is just a very, very tiny part of the Chromium architecture. Chromium is massive. The whole thing is massive and much bigger than you imagine. So this is very, very small. And the problem, of course, is making diagrams is that this is a quote from myself. I made it myself. Somebody should put it on Wikipedia. At a high enough level of abstraction, everything looks the same. So basically, it's the law of PowerPoint architecture, which basically means if you just boil it down enough, high enough, there's one box and there's an arrow to another box. And just pick a name and put it on the boxes and you're finished, and that's your system. So to try to get around this, there are boxes and there are arrows, but it's difficult. So first, like I said before, you have the actual decoding. Now, an interesting concept, which I will talk a little bit about in the next presentation, is the fact that network access is not available inside of the renderer. Now, the renderer actually runs the web view, and the web generally comes from the internet, right? So that makes it interesting because the actual network traffic comes through the browser process and has to be piped over to or transferred over to the renderer process. And this is true also in this media stream, right? So the media stream comes through the network stack in the browser process into the decoder, which is in the renderer process. And the decoder produces this video frame with a YU and V plane. And it's in memory. So Chromium has this idea of a reference to this type of sync token, which they call a mailbox. And then you have also something called a mailbox holder to hold the mailbox and a sync token and a text or target. I'm not going to go into this. You can look at it if you want to. But you'll get a lot of boxes with those names, so I just mentioned it. But basically, on the left-hand side here, you have our wonderful video frame with our buffer, and that's great, but we need it over on the GPU process. So we're going to copy it into shared memory. Then we're going to have a reference to that, but it's sort of like a vague idea, and we'll look at it. But it references this thing that we have copied into shared memory. And then this thing that we've copied into shared memory will be uploaded to the GPU as an EGL image. And then later on, we will say, paint that here on this clip rect. Yeah. So in the preparation is all about trying to make all of these types of resources and make sure that they're registered in this transferable resource thing, which is basically a little struct that you can carry around. And it ends up here. So now we're going to try to paint. We've gotten this YUV video draw quad. So now we are going to try to paint this thing, but we're still referring to something that we don't know exactly the state of. We don't know if it's all already uploaded on the GPU or whatever it is. We're just referring to some conceptual thing that might have happened or not. And to make sure that our draw commands, because here we're going to actually make a shader, we're going to have a GL program, we're going to say we want you to paint this thing with this ID, blah, 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 but we don't know if it's done. So to make sure that our commands come after the upload, we have to connect to the sync token, which was issued when we copied it over. And then you have the render, send the clip region, and it's like, whoo, and everything's good. Now, this is a very, very simple thing. I'm drawing an opaque square image I had in memory. And now you looked at the CSS earlier, and there were like hundreds of them, right? So this is a massive architecture. So this is what we've tried to do. We issued some commands, then we put in a sync token, then we put in a waiting sync token, and then some more commands. And then we're hoping that, this will make sure that the little yellow one pushes the other one out, before the top blue ones get processed. But the thing is, this is not really done with out-of-the-box OpenGL ES2. Of course, they added extensions to do their special things, and they actually have a bunch. And these are only 3. Which are used in this example. So they make their own OpenGL ES2 extensions to be able to handle this, and even more boxes. And you can see that here. So basically, you have a regular bind texture that you see on the right, and then you have this create image Chromium in the middle, and then you have this bind text image 2D Chromium. So they are not using out-of-the-box OpenGL ES2 either. They have their own extensions. So, okay, so I talked a lot about this in Chromium, and it's kind of interesting if you have a Chromium-based browser. It's kind of like, okay, I know that now, but why would you even care about this? Because, why aren't you just doing, why wouldn't you make a separate GPU process to handle all your GPU commands? Why wouldn't you at least have it in the browser process? And, well, yeah, actually on Android, Chromium actually has it in the browser process. It's in a GPU thread. And that is also the architecture that Qt chose for Qt Web Engine. So they also run GPU access in a GPU thread. But they have their reasons, and we'll look at those. And those reasons might not be your reasons. But let's see. So first of all, security. Like I said before, you've had access, you've had issues and bugs in the past, and I'll show you a couple, of texture memory being leaked. So either that it's being leaked across tabs, so another web page might be able to read texture memory that you wrote in your tab, which could leak personal information. Other programs might be able to read texture memory that was written by Chrome, which might have, or your browser, which might have personal information, like your passwords or whatever. Because these are just pictures, right, that need to be rendered. And all of these steps give you fine-grained control where you can insert many things. You can zero out memory whenever you want because you have so many steps where you can insert your own code in this pipeline. Because there's no actual real GL calls until you decide to do that. So this is one example where somebody took and just painted what was in texture memory on a cube in a web page. And that might not be something that you'd like. And here's the other way around, where someone is taking texture memory that Chrome had painted on and pulling it out in another application. Again, something that you might not like. So the fine-grained control is one aspect. But then you also have the fact that these Chromium-based browsers have to run on very, very different hardware. They don't know what hardware they are. Many different operating systems, many different hardware, many different GPUs and graphics drivers. So this is a very complex landscape where you have to deal with other people's bugs, other people's implementations. And graphics drivers do crash on occasion. And especially now that you are running basically GL that you are getting in WebGL, you're getting GL commands from the internet, right? That you are executing on the user's GPU. And so vulnerabilities in the GPU or in the GPU driver suddenly become your problems, right? So in this case, you have many places where you can choose to bypass the GPU, and there are many software fallbacks. And I will, let's see. Okay, let's look at that right now, actually. So if you go to your browser, in this case is, let's see, it's Vivaldi, and you can go to Chrome://GPU or whatever for whatever Chromium-based browser, and you will see that you have this page where you have driver bugs, workarounds, problems detected, references to bugs. All of these places are places where Chromium goes in and looks at stuff, and you will see up here that you have many different kinds of fallbacks. In this case, I have hardware for many things, but here it's software only, hardware acceleration disabled. And my point is, this is quite complicated, and but they have that opportunity because of the pipeline being so exposed. Before you choose to do the call, you can reroute it to other things. And then you have dependency separation. You might have a driver that is loading shared libraries into memory that you don't want to have inside of your render process or inside of your browser process, things that you don't trust. And So to put it out in its own process, you are also putting it into its own memory, and it's not accessing your memory, and you can make more isolation possible. Also, the render sandbox would be completely broken if you loaded a GPU driver or a graphics driver in there, because graphics drivers sometimes need access to the internet. There are like all sorts of things that this graphics driver would need. That means you basically had to disable the whole sandboxing. Performance. I don't know. They say it has a performance advantages, basically because of what you saw before. So you could issue the commands to say, you know, I want you to upload this texture, but you don't really have to care about it, and then later you could do it, and then all sorts of different processes can do this at the same time, and they feel they're introducing a form of parallelism that gives you an opportunity for better performance. I don't know. The thing is that a browser is generally used to running on really good hardware. So these things might not be true on your device. So this is another good quote. We can solve any problem by introducing an extra level of indirection, except for the problem of too many levels of indirection. And this is if you are going to look inside of the Chromium source code, this is something that you will feel deeply often. Because, like I said, you have such a diverse set of hardware that you have to run on. There are so many layers of abstraction, and it becomes really, really hard to follow. And this is true for basically any part of Chromium. So, can I use? I don't know. The thing is that this is not really, it's not a prepackaged thing. It's not a library you can just take in. This is something that has been specially engineered for the exact use case that Chromium has. But you might have a similar use case, but probably your use case is a lot easier. You have known hardware. You have a known architecture. You have a known operating system. You can actually, if you're going to work around bugs in your driver, you have one driver. All of these things makes your need for complexity a lot smaller. So it's not exactly cut and paste. And like I said, you can go and check your browser and the GPU page, and you will see exactly how much control they have inserted in this system, and you might not need that at all. Because they're using OpenGL ES2, and that's fine, but they also use their Chromium extensions. And in addition to that, they have their own APIs, their own IPCs, where they can also communicate, right? So all non-trivial abstractions, to some degree, are leaky. They are trying to make a normal OpenGL ES2 interface that you are programming against, but it is normal in quotation marks. Okay, what can I use? I'm a consultant now, so I'd probably advise against it. But knowing that it can be done has value. Because that is one of the things, when you're trying to solve a problem that you don't know if it's possible at all, if you know that somebody has done it, even though you don't know how they did it, you know that it can be done. And that could have value when you choose you're going to try this thing. You're going to dedicate a month to try this architecture because it might solve a problem for you. So knowing that it can be done might have value. And so, maybe. And that's my talk. But I have a little bit on the end. I have another talk. It's on YouTube. It's called Deconstructing Privilege. I made it at NDC also in June. And I would really like you to watch it. It is a non-technical talk. It's my pin. It's fabulous. The link to it is on my pinned tweet on Twitter, and I would really appreciate it if you took the time to watch it. And that is my talk. Thank you. Now we do have a little time, so if you want to ask me while I pack up, we can go and do that. Okay, I'll pack up now.